Hi, good afternoon. I'm Mark Brooker, and today I'm going to be talking about or taking a deep dive into Lambda function security or Lambda function isolation. Over the course of this talk, I'm going to dive into the technology that isolates one Lambda function from another and touch on some of the implementation details behind some of the new features for Lambda that we've launched over the last few months, including container support and extensions. One thing that's worth understanding before we start this talk is that you don't need to understand any of this stuff to use Lambda scalably, or to even use Lambda in the most secure way. These are internal details for people who are really looking to get into the middle of the system, and not something you really actually need to understand. This is one of the big benefits of serverless, because you don't have to be a deep expert in the way things are designed to be able to use them at scale and securely. I'm going to dive into a few things in this talk. First, I'm going to talk through the function isolation overview, how functions are isolated from each other. And during that time, I'm going to touch on Firecracker, our open source VMM, and I'm going to talk a little bit about extensions. Then in the second half of the talk, I'm going to talk about the Lambda container support that we recently announced, and some of the implementation details and security details behind container support. So let's start talking about Lambda function isolation. Firstly, what is Lambda function isolation? Why is this an important question? Well, if you look at the tiny yellow orange dot on the right-hand side of the slide, that is the smallest Lambda function that we offer. It's 128 megabytes of RAM. And that's a very, very small dot. And then the huge yellow orange dot on the left-hand side of the slide is a typical data center server. In this case, is an EC2 M5 instance. And this is very typical of a modern data center design. This thing has 384 gigabytes of RAM. It has 48 cores, 25 gigabit networking. Very typical numbers for a modern large machine or modern data center class machine. And so the problem that we have, and partially the opportunity we have, is that we can fit hundreds or thousands of these smallest size workloads onto a typical machine. And that's a problem because we need to figure out a way to do that securely, and we need to be able to do that with great performance and great scalability. It's also an opportunity because being able to put so many different workloads on a machine allows us to offer the scalability and performance of serverless by taking advantage of the fact that a single function is quite small compared to the whole fleet. And so we can scale it up and up and up and up with very few restrictions and very few limits. So let's look at the details of how this works. Here's a basic stack showing just two functions running on the hardware. In reality, there'll be hundreds or perhaps thousands of functions running on a piece of hardware. So down at the bottom is an EC2 bare metal instance. We run Lambda on EC2 instances, just the same kind that you can purchase. On top of that bare metal instance, we run a host operating system, Amazon Linux. This host operating system, an operating system kernel, provides some of the virtualization support that we use to separate each function from each other. Then we step up into the dedicated part of the diagram, where each function and each concurrent invocation of each function has resources dedicated to just that invocation of just that function. And the resources that are dedicated to you is a Firecracker process, and I'm going to talk in detail about what that does and how it fits into the stack, and a micro VM. This micro VM is an entire running hardware-backed virtual machine that is dedicated to each concurrent invocation of every function that you run in AWS Lambda. And inside this micro virtual machine is a guest kernel. There is a runtime like the JVM or the CLR or whichever other language runtime like Node or whatever you bring. There's a Linux guest kernel dedicated again to each concurrent runtime of each individual function. There's all your extension code. So if you're writing extensions with the new Lambda extension API, you get one copy of that extension, of every extension you write, inside each micro VM, completely isolated from everything else, using the same security model as applies to functions and runtimes. And finally, you get your own Firecracker process that is creating the micro VM, managing it, and performing I/O and so on. So what is Firecracker? Firecracker is an open source virtual machine monitor that is purpose-built for creating and managing secure, multi-tenant, container, and function-based services. And so what this means, if you're not an expert in virtualization, is that we went and looked at all of the different technologies available for virtualization and for isolation of customer code on machines, and we didn't like any of the options that were open to us. So we chose to build from the ground up, or build a purpose-built technology for managing, or purpose-built for serverless and for container workloads, virtualization technology, and we use this technology as the basis of our isolation story in Lambda. And so the Firecracker process is the piece of the stack that is responsible for setting up the hardware that does the heavy lifting of virtualization, and for handling I/O and other details. And so it fits into the stack like this. Here, the dotted block of the diagram is the micro VM. This is the really strong security boundary provided by the virtualization hardware. Inside that is two layers. There is the user space, which we call untrusted code. Well, this is code that you trust. It's your function, it's your extensions, it's your libraries, and so on. But it is not code that we trust. And that is because we don't want any other customer to have to trust your code, and we don't want you to have to trust any other customer's code. And so we treat all code that lands on Lambda as untrusted and unprivileged. This runs on top of the dedicated guest kernel that runs inside each micro VM and has rich access to all of the, or most of the APIs of that kernel, and can run just like normal Linux software. So this is just regular processes running on top of a regular kernel. Then there are the interfaces from the secure micro VM to the outside world. And there are two sets of interfaces here. First, there are the interfaces that go straight out to KVM and straight out to the hardware. And this is kind of the low level near the silicon stuff, like page faults and model-specific registers and saving and restoring register state, and a bunch of other kind of very low-level, but very important, well-understood details. The more complex stuff is handled by your dedicated Firecracker process. And most importantly, this includes networking and disk I/O. So whenever your process or your code running inside this micro VM tries to send a packet out over the network, receive a packet, write to disk, read a file from disk, that traffic is going through the Firecracker process. The way that works is that the guest kernel provides those interfaces, just the read and write syscalls that you're used to, and those are backed with a special driver called a virt.io driver. And virt.io driver talks a special protocol to the Firecracker process over a small amount of shared memory. And the Firecracker process takes the packets and the IOs and all of these other things that are sent by the guest process. It sanitizes them and makes sure that they're in the right places. It makes sure they're going to the right places. And then it passes them on to the host kernel as send this packet, receive a packet, write a block, read a block, and so on. And so Firecracker implements this kind of the back half of a virtual hardware device, virtual block device, and virtual network device that is presented to the stuff running inside the micro VM. So it's kind of a hardware emulator of sorts in a simplified mental model. And so the way this fits into the picture is that you have, again, this dedicated per function or per concurrent invocation of each function, micro VM, and Firecracker process. And I want to talk a little bit about some of the additional layers of security that we've built into the system. And again, the micro VM, using this powerful hardware-backed virtualization technology, provides the primary security boundary. But it's always a good idea to have multiple layers of security in a well-designed system. And so the first layer of security I want to talk about is an inner sandbox. So inside the micro VM, we take the function code, the runtimes, the extensions, and other similar things, and run those inside what we call the inner sandbox. This inner sandbox does two things. One of them is it provides us a convenient place to hook in operational metrics and some of the metrics that you see out of your function in CloudWatch. The other thing it does is it allows us a place to cut off access to little bits of the guest kernel that we don't think normal functions want to access. And this makes some classes of attacks harder and improves our security resiliency. Then there's another layer of sandboxing, and this is something that we call the jailer. So I talked about how Firecracker takes all of those IOs, so all of the network packets and the reads and writes that you're doing, and passes them on to the host kernel. The set of things that a Firecracker process can do, at least once it's fully set up a VM and is just running and processing packets and IOs and so on, is actually rather limited. And so we take advantage of that property that a Firecracker process shouldn't be doing much at all, and we put it inside a very restrictive sandbox called the jail. This very restricted sandbox even further limits what a Firecracker process can do by accessing the guest kernel. It cuts it off from parts of the disk, it cuts it off from almost all of the surface area of the host kernel, and limits its privileges greatly on the host. So in the very unlikely event that your code is compromised, and that an attacker is able to get through the guest kernel, get through the virtualization layer, and run code in the Firecracker process, they're faced with a very restrictive guest kernel. So again, that virtualization boundary, that micro VM boundary, the dotted boundary in this diagram, is the primary security boundary, the one that you should be paying most attention to. But the inner sandbox and the jailer provide an additional layer of protection in the architecture. And because Firecracker is open source, you can go on GitHub and see the allow list that we use for controlling access to the host kernel using the Firecracker jailer. Now that we've talked about isolation, let's talk about Lambda containers. As you probably know, just a few days ago, Lambda announced support for bringing functions as container images. This is very exciting. It's something that I'm super excited to see launched, and can't wait to see the things that people build with it. But it also presented my team, as we were engineering this, with a set of challenges and a set of opportunities that we needed to figure out how to get around. And so what we've done is we've built into, we've modified this architecture by adding a new per micro VM dedicated component that we call the sparse file system. And so this is a component that sits next to Firecracker on our machines and handles I/O, handles reads and writes to the disk, and provides an extra layer of virtualization and provides us with an extra layer of control. Let's talk a little bit about why that's necessary. If you're familiar with the Lambda function zip model, Lambda function zips can be up to 250 megabytes in size, whereas we support container images up to 10 gigabytes in size. That's 40 times bigger. So for a container image, you can, for a zip, Lambda downloads the whole thing onto the worker before we start executing your code. However, if your container is 40 times larger, you don't want to wait 40 times as long. And we wanted Lambda container support to feel just as instant scaling and just as serverless as Lambda zip functions. And we weren't willing to compromise on performance. So how did we get both of these things? Well, we made some observations about what goes into a container. First, containers are often based on common base layers. These can be the base layers that we provide for Lambda. They can be some of Amazon's provided container base layers, or they can be open source base layers that are very widely used. And base layers tend to be widely used. You tend to have a base layer, a common base layer across a whole company, common base layers that contain things like extensions, things like monitoring agents, things like libraries, data sets, AI models, all sorts of things that are shared or potentially shared across lots of functions. And of course, there are the common and popular open source base layers that provide the base of a majority of containers. And so there's a big kind of common set of this large chunk of data. The other property of it that we paid attention to is that it's sparsely accessed. It's very unlikely or uncommon for a function to look across a whole file system and touch every single file or touch every single block on disk. It's much more common that a function starts up, it reads some files to start up a runtime, it loads some libraries, and it loads a data set, but never touches the majority of what's on disk. There are libraries, there are binaries, there are other data sets, there are log files, there are all sorts of things on disk that typical container workloads just don't access. And in fact, if you look at container workloads, it's not unusual for a function-style container workload to touch only a few percent of the blocks on disk, or to read only a few percent of the blocks on disk. And so that provides us with a great opportunity to optimize load times. So what we do is we take a container and we chunk it up. We break it into lots and lots of small chunks. And then we load those chunks on demand when you read from a piece of the file system, or when we predict that you're likely to read from a piece of the file system, instead of loading them ahead of time. The benefit of this is that your code can start running much, much quicker. And if you have files or binaries or libraries or other things that are making your container image large, those don't add weight. They don't add delay. They don't add time. If you're not touching something, it doesn't cost you load time at all. And that's a great property, because while for all kinds of reasons we want to look at container images and we want to take out as much as we can out of them to keep them as simple and basic and small as possible, and that's still a best practice, but it's also a difficult thing to do, and it requires a certain amount of investment. And so what we wanted is that you could use the containers that you're used to, with the base layers that you know and have experience with, in Lambda, without the extraneous things that might be around costing you load time. And using demand loading and using predictive loading of chunks of the file, instead of loading an entire container image, allows us to do this with much, much fewer compromises. So let's step a little bit into how that works under the hood and some of the security properties, which are really the point of this talk. So here I've turned the stack over a little bit. We have the Firecracker process on the right-hand side. And again, that Firecracker process is getting the reads and writes and those I/O requests that are coming in from your micro VM. So your function code is saying, read this file, write this file. It's going through your guest kernel and landing at that Firecracker process. That Firecracker process is then passing off these reads and writes to the local sparse file system agent. Inside the sparse file system agent are three important pieces. There's a dedicated local cache that provides a dedicated cache just for your micro VM of commonly read disk areas. So they're kept nice and hot and nice and fast to access. Then there's a write overlay. So all of the writes flowing in from your function code through Firecracker are handled here in the sparse file system agent. The sparse file system agent also integrates with KMS, and I'll talk about why that's important later. But that's so it can handle your keys and make sure that it's the first place in the system that has access to the plain text of your data. Then, when the local cache is missed by reads, there is a shared cache that is on each machine. And again, very fast access because we have fast local storage on these machines. And that is shared across multiple sparse file system agents. And then we have a per availability zone shared local cache, which has an even larger directory of chunks. And because of the speed of the EC2 network that we use, loading from that local cache is still very, very fast. So let's step into one of the security properties that I think is important here. These shared components, the shared local cache and the shared multi-AZ cache, only ever have access to the ciphertext of chunks. They never have access to chunk plain text. And they only ever are read from. They're never written to by any of the Lambda workers. And so they're just a read-only store of encrypted chunks of data. And this is a great property for something that is shared across lots of workers and shared infrastructure that is used by many, many workloads. However, the dedicated stuff, the stuff that is per micro VM or per concurrent execution of each function, has access to the plain texts of your function, of your container. And the reason it has to have access to the plain text is when you read a file off disk in your container, you don't want to get an encrypted version of that file. You want to get the file itself. And that's done with a sparse file system's integration with KMS, where it uses KMS to decrypt the data that is stored encrypted in the shared components. So how did we take advantage of all of the sharing that is sort of inherent to containers because they have these common base layers? Well, we do that with a process called deduplication. We want to take lots and lots of containers and we want to extract the common data. So we want to keep your special data completely isolated and the data that is shared with other customers or other containers in your account, and we want to separate those two. And we do those with a cryptographic procedure called convergent encryption. We take each chunk of data and we use a keyed hash and some other techniques to extract a key from that data that is deterministically calculated. We then encrypt that chunk using modern strong encryption techniques, and we take that key, that chunk key, and we build it or we put it into a manifest. And by manifest, I simply mean a list of chunks, where they're laid out on disk, and what their unique keys are. We then take that manifest and we seal that manifest. We encrypt it with a modern authenticated encryption cipher using your KMS managed key. And so you have all of these data chunks, each one with its own unique key, and then this manifest sealed with your encryption key, which contains the keys of all of those data chunks. This scheme allows us to offer secure deduplication without any component having full access to plain texts. In fact, only those local agents have access to the plain texts of your container data, and they have to do that using your KMS key. There's obviously a lot to the scheme that I haven't been able to explain here, but it is one of the key pieces that we built to make sure that Lambda container support is just as fast, just as scalable as Lambda zip-backed functions. There's a lot to security, and so I want to recommend some other things to read and watch when you're done with this talk if you'd like to learn more. First, I'll start with a security overview of AWS Lambda. This is a frequently updated overview that covers our security implementation, so it should cover everything that I talked about this talk, but also covers a lot of best practices I haven't gotten to here about how to use Lambda securely and how to put it into your architecture. You'll find that document on the AWS website in the white paper section, and we update that frequently, so refresh it from time to time if you'd like to learn more about the kinds of work that we do. A lot of people, when they ask me about serverless security and ask me about multi-tenant, ask about micro-architectural side channel attacks like Meltdown and Spectre. These are deep, deep topics of their own, and I haven't had the time during this talk to talk about them in any kind of detail. And so I would recommend that you go and watch this talk from AWS reInvent 2019 called Speculation and Leakage, Timing Side Channels and Multi-Tenant Computing. In this talk, my colleague Eric Brandwine gets into real detail, like down at the assembly level detail of how these attacks work, what the risks are, and just some of the mitigations we use at AWS to make sure that we are fully protected from them. And then finally, if you'd like to understand things at a really academic level, we wrote a paper earlier this year at a systems conference called NSDI. That paper is called Firecracker, Lightweight Virtualization for Serverless Applications. And it dives into the details of how we built Firecracker, how the technology works, what trade-offs we made, how we compared it to some of the other virtualization and isolation security systems that are available, and how it is used inside Lambda, and some of the things that we see as challenges in this space for the future. So if you want to get real deep, there's 12 pages of small text there, and lots of diagrams and other fun stuff. So be sure to check that out. Thank you very much.